CryoTrack is a tool for assisted non-invasive surgery. It helps the surgeon through real-time needle trajectory planning and correction. It also takes into account patient breathing, but I won't be showing it today because this is a feature that is under development. So the different parts of CryoTrack are first an EMT, then a computer on which we run CryoTrack, which is an extension of 3D Slicer, and of course our model of a patient here. The model of a patient is called a phantom. Its matrix is out of agar-agar gel, and it contains here in dark and black a bone structure which is flexible in order to be able to simulate breathing. Inside we have in blue a risk structure which is a trachea, and we have small colored dots which are targets. This whole model has been scanned. We have it in 3D on our computer. Then we have here, as said, the EMT, electromagnetic tracker. It is composed of the main unit. Then we have here an emitter and two trackers. The bigger tracker is fixed to the surgical needle. We use the bigger one because it's the most precise one of the both, and it has also a bigger range of detection. The smaller one we use as our origin, world origin, to which we track all the points. So we fix it to the patient. On our patient here, we have a spot that doesn't move when breathing, so we put it here in the back. This is a part that doesn't move. So this makes it the whole system agnostic to a patient translation and rotation. First of all, before starting CryoTrack, we need to switch on the Trackstar, the EMT. Once this is done, we go into the root of our project, and in which we have a driver for our EMT, which allows for communication between the EMT and Trackstar. The communication is done through IGT-Link. It is a protocol used for guided therapy through imagery. So once you have compiled the driver, you can launch it. It is ATC IGT-Link server. Just run it. Let's open another terminal, and here we have inside of the project a script that launches CryoTrack. It launches 3D Slicer and then launches CryoTrack, which is an extension for 3D Slicer. 3D Slicer is a tool for medical imagery. Now, let's start the script. It is called CryoTrack Launcher. Here we go. And on the left, we see that the sensors have connected, the two. And it's just awaiting a client. The project of CryoTrack is focusing on automation of all the steps. So the setup, it doesn't take long. It's only 5 minutes. And as we will see here, we immediately come onto the page, onto the interface of the extension, CryoTrack Planner. And as we can see, everything is listed here, so the user does not have to go into other menus of 3D Slicer to calibrate, to set up his project. So now we are ready to start. First of all, as I said, we have a 3D model of the patient. Let's first import it. Here it is. Then we have our needle here. It is detected but not calibrated. So one thing you could do is import a needle calibration you have already done, but what I suggest is to calibrate the needle. It could be that from one session to the other, the emitter has heated to a different temperature, and then you have to do the calibration again, things like that. So let's do a calibration. It's very fast. First, before doing this, we have to create a surface that is non-slippery. What I suggest doing is just putting tape here in order to be able to lock the tip of the needle on this material. Here. Now, let's take the needle and calibrate it. So put it here. The first calibration step is pivot calibration. Let's start. And once the calibration is done and we are satisfied with the square error, we can just stop when complete here. Let's say that 4.5 is enough. Here, very good. And as you see inside of the view here, we have our needle that is at the correct length. Then let's do spin calibration. It only takes seconds to do. And once we are satisfied with the error, let's say 0.5 is very good, then we are okay. Let's go back to the extension of a CryoTrack. Now the next step we have to do is to map the points that are defined, how they're called. The calibration points I've set on interesting markers on the patient with our needle in order to calibrate the model inside of the simulation. So here we can see on the interface that we first have to set the point of the spinous process, which is here, down there. Let's put the needle on the point on the phantom and just place the point. Once this is done, we go to the next point here. It's the rib 8 on the right side of the patient. Here. Once placed, we just click place point and go to the next one. Next one is a bit tricky. Yeah. Next. Now, rib 8 left. Placed. Next. And another one. Up there. And placed. Now we have all the points. If we, let's say, are not liking our placement, we can just reset. We have a good set of points, so we calibrate the model. This then places the model correctly so that when we place the needle in real life on one of these points, it is also placed correctly inside of a simulation. Now that we have done the calibration and the setup, we can go on to a surgery. So now that everything is calibrated and set up, we can go on to select the different risk structures and bone structures. So as you can see here, we have the trachea in our case, but you can also select multiple ones for the simulation. And for the bone structure, we have here the thoracic cage. And let's also select a target. Let's say target number 2. In CryoTrack, we have a handy tool which allows us to generate a map of potential insertion areas. Let's generate them. This is done through the generation of a convex hull around the patient, so the surface of the patient, and doing ray tracings from each point towards the target and looking for potential intersections with our wrist structures or bone structures. As you can see here, we have a big area where we cannot insert because each of these points go through actually the wrist structure, which is the trachea here, before going to the point. So this means that each point here of insertion will not be possible because the insertion would go through a wrist structure. Let's look at target number 1. We have also here an example where we can see this. This time it is on the left. Here we have a patch. This means that if we place our needle here, we cannot go to our target without passing through a risk structure. Also, we can see here we have the bone projection here on this insertion map. So we cannot here insert without going through bone. Let's do a surgery. Let's select, let's say, the point, the target number 5. Let's first generate the insertion map to know where we can place our needle. This area right here looks promising. So once our needle is placed, we just click Needle Placed. This will make our model translucent so that we can see the targeting ring here. The targeting ring is an intuitive approach to needle trajectory correction in real time. So the idea is that our needle, the end of the needle here is projected onto the plane that is defined by the normal of the vector going from the needle tip to the target. Meaning that we have to align the needle with the trajectory of the needle tip to the needle to the target in order to make the ring very small. Once the ring is small, we can be confident that we are on the right path towards our target. The concept is that we have to keep this ring as small as possible during the whole insertion. And we will most definitely hit our target. Let's start. Keeping the ring as small as possible gets harder and harder the closer we get to our target. And this is a hit. Let's do another target. Let's say target number 6. Let's generate the map. This area of entry looks promising. Let's do our surgical procedure here. We have placed our needle and let's keep the ring as small as possible. And we start. We are there. Now let's do a quick overview on how the patient model is structured as a file. So here, all of this here is the patient. We have here a folder with all the models. We have the targets, we have the bone structure, and we have here the risk structure, which is the trachea. Then we have a folder with all the calibration points that are set manually in the file. If you discriminate the model, meaning you reduce its poly count, keep in mind that in order to place the calibration points correctly, you have to do it on the initial mesh, because the discrimination of the mesh reduces its size. So if you place points on the reduced mesh, it won't represent the real configuration well. And you will get erroneous calibrations, wrong calibrations. This is how a patient model is structured.